Okay. Hello, everyone. Welcome to the speaker session of the day. Today, we're going to have an amazing speaker that I'd like to welcome. So today, we actually have Ovia Seshadri, who is a student at the Department of Computer Science and Engineering at the Indian Institute of Technology, New Delhi. She recently submitted her PhD or dissertation titled Securely Improving the Performance of Proof of Work Blockchains. Prior to her PhD journey, she gained her master's in software engineering and worked as a data warehouse modeler. So she is an absolutely amazing speaker. She is incredibly interested in blockchain, distributed systems, databases, and networks. And just currently mastering NPC. I'm not sure what NPC is, but I think Ovia can tell a bit more about it herself. So Ovia, welcome. We're incredibly excited to have you on board, and let's get started.
Awesome. Thank you for the lovely introduction. My name is Ovia Seshadri. So right now, I've just submitted my PhD thesis. I'm working as a researcher for CoinDCX, which is a crypto exchange in India. So MPC actually means multi-party computation. So it's kind of like a sister or a relative of zero knowledge proofs. So maybe you might have heard of that. So shall I start with the session today on consensus?
Let's start. So I'm going to start recording now.
Yeah.
And feel free to share your screen and let's get started.
Awesome. Yeah. Let me just share my screen. Okay. Yeah. I'm going to start. Can you all see my screen?
All good.
Yeah? Okay, cool. Before we start, I want to quickly know how many of you have worked in computer science before? And just like a show of hands? Maybe you can I can see a couple of hands. So there are people with non-technical, non-computer science backgrounds here as well?
So right? The majority are actually with non-technical backgrounds.
Okay. So those who are from computer science backgrounds, even non-technical backgrounds, are you familiar with blockchains? I'm just gauging the audience here right now. So it doesn't matter if you are, I will try to break down all the jargons for you, but just to know. Yeah? Okay, cool. So I see a couple of hands up. Okay, doesn't matter. So please I want this to be interactive. Please feel free to stop me at any time if you don't, if I'm going too fast or if you don't understand a word or anything like that, okay? So I'm here to talk about arriving at a consensus in a global distributed world. That's a mouthful, so let's break it down. Okay, cool. So what is consensus, right? Let me just, cool. What is consensus, right? Consensus is nothing but coming to an agreement among a group of people, among a group of systems, computers, between computers and humans. It can be anything. Just when there are multiple parties involved and you want an agreement or a decision between them, that's what consensus basically means. Okay, and what's the consensus mechanism? It is the set of steps that you have to follow to achieve consensus. Okay, consensus is omnipresent, in my opinion. It is an integral part of our society because we humans are social creatures, right? We have to live together, so we have to agree on certain things. So we need consensus. It's there in governance, it's there in democracy, it's there in politics, it's there everywhere you see. Like simple, even our notion of time. Okay, for me, I'm in India right now and it's 8:30, and there is somebody, we have come to a consensus on how we calculate time and what time each of us should follow. Okay, if you look at like air traffic control, for example, You're at the airport, there are so many things, there are so many flights, there are so many people that have to work together to make things efficient and smooth for the passengers. And there's a lot of consensus happening there, right? Even in academia. Okay, so if you're to get something done, right? If you're publishing a paper, writing an article, you submit it somewhere and they elect a group of experts to agree on whether to accept your paper or something. So there's consensus everywhere. And in the digital age, we're using our mobile phones. We want things to be fast. We want things to be secure, reliable. So in distributed systems, in distributed computing, consensus is a very important aspect. And even more so in blockchains and Web3, where in distributed computing, you have a group of trusted computers which are geographically distributed, who have to come to a consensus. But in blockchain, you have geographical distribution as well as people who don't trust each other. So consensus becomes very important over there. So that's why consensus is a big deal. But it is not easy to achieve. Okay, so why is it not easy to achieve? Firstly, there are multiple parties involved and you want all of their needs met, right? You want majority in agreement and satisfied with the decision taken, which is the output of consensus, right? So it has to be fair to all the participating nodes. So, and that's one part of it. Among many people collaborating in consensus, there can be some adversarial nodes as well. You can have people who want to turn the decision in their favor by unfair means. So you have to deal with that. And the next point is the nodes that are participating in consensus are geographically distributed. They're not in the same room where they can just talk to each other and communication is fast. No, they're geographically distributed all over the world and they have to talk to each other. And when they talk to each other, they send messages, and messages take time to go across the internet. And in that time, anything can happen. The network may fail, the packages can be dropped, somebody can intercept it and change the content of the message. Anything can happen, and we should be ready for it. And networks can be dynamic. What does dynamic mean? So in blockchain network, especially, in general, for example, when in our government, when we vote for the next in our next election, they conduct a poll, they conduct a citizens poll. They know how many votes to expect, and they know who are what. So that means the network is known a priori. The participating nodes are known a priori, and it doesn't change. But it is not like that in blockchain, for example. Anyone can join the network and anyone can leave the network at any time. So how do you make sure that people participating are there for the entire consensus duration and they don't leave in between, or new nodes don't get added in between? So networks are dynamic and extremely, extremely large. So permissionless and master slave. So as I said, in distributed computing, you have nodes that know each other trying to come to a decision together. But in blockchain, there are people who you don't trust. There are nodes that don't trust each other and they have to come to a decision together, which makes it even more difficult. And scalability. So coming to a consensus between 10 people is much, much easier than coming to a consensus between, let's say, 1 million people, right? Million nodes. So the scalability massively affects consensus. So there are so many problems. Consensus is very important. We need it, but it is not an easy problem to solve. Okay, so let's look at what exactly we need, what exactly consensus should include, right? Consensus mechanism should enable participants to cooperate and work as a collective, allowing them to collaborate towards finding an optimal outcome that puts the interest of the entire group first, right? The process should be inclusive such that many people are involved and actively participating in an egalitarian process, and all of their inputs and decisions are equally important. Okay, and we also want that the decision and the consensus is useful, right? We can easily say, let's just all agree to make the decision as one, or just say yes, but that's not of real use to anybody. right? We need the consensus to have a particular input. People decide based on that input and give a output decision collectively, right? And that everybody accepts that output. So this is what we want a consensus mechanism to be. So putting all of these ideas together, let us define some technical requirements for consensus mechanisms. Okay, so now we put these, we've jotted down 4 technical requirements for a consensus mechanism. Any consensus protocol that adheres to these requirements are resilient to Byzantine failures. So we will talk about what Byzantine failures means, but let's first look at what these requirements are. First agreement, right? Everybody who participates should agree on the decision that is made. Final decision everyone should accept it, right? They can't say, no, I don't agree. I'm not going to follow these rules at the end. If they participated, and if according to the rules of the consensus mechanism, if the decision is being taken, they have to agree to it. Second, termination. Every consensus mechanism should terminate. That is, ultimately, some decision must be taken. It cannot be that after participating in the algorithm, there is no decision. Third is validity. Okay, if I'm participating honestly and I've been given an input, two honest people who've been given an input should get the same output if they followed the same steps, right? Fourth is integrity. Integrity means if all the honest people are producing some value, then that must be the final decision. It cannot be that honest people produce some value, and let's say somebody has changed the algorithm and an adversary can influence the final decision, right? So these are the requirements for a consensus mechanism. Is everybody clear so far? Please feel free to unmute and tell me what you think, or if you have any doubts. Okay. All right. So I'm going to go ahead. So we saw this word called Byzantine failures. What does that really mean? Byzantine was actually, let's say, like, it was a civilization long back that happened right after the Roman Empire. So all of this Byzantine failures started off but with this 2 general problem, or Byzantine general problem. So I'm going to talk about this with you today. So in the Byzantine era, there were Byzantine generals, there are Byzantine armies basically. All of these are Byzantine armies, and they want to attack some city which is in the center. Okay, so this city is a very powerful city, and they have like really good protection and high walls or good army, right? So the Byzantine generals have strategically positioned themselves all around the city, and they should attack. Okay, so it is an agreement problem on how to attack the city such that they can conquer it. Okay, but it has some challenges. Firstly, the enemy city, as I said, is very powerful. They have a very good army. So only if all the generals attack at the same time can they conquer the city, right? The second challenge is that these generals have already positioned themselves in strategic locations, and they cannot meet, right? They cannot come together to decide on a plan on when to attack. So they have to communicate from their positions by sending messages to decide on a particular time to attack this city. But there are other problems here. So the messages could be interpreted, they can be changed, the messenger could be killed. It can be replaced with another message. There are significant challenges here. Okay, and this whole thing is further complicated by some generals turning traitors. Okay, so this whole we should develop an algorithm such that the city can still be conquered even if some of the generals are traitors, right? So yeah, there's a lot of stuff happening here. So a consensus mechanism that is able to achieve the conquering of the city is Byzantine resilient. Okay. So there are we can broadly classify consensus mechanisms in 2 ways, iterative and non-iterative. Iterative consensus means that a group of people come together and they talk to each other in an iterative way. That is, I tell you something, then you reply to me, and then I decide something, I share that with everyone. Based on that, based on my data, they make another decision and they share it with me. So with some communication, we arrive at a decision in an iterative way. Okay, this is a very good way to come to consensus for smaller networks. Okay, but it takes high bandwidth because we have to constantly keep communicating and exchanging data with each other in order to come to consensus. Okay, it will take more time, but it is optimal for smaller networks and it is more secure. That is, more secure, I mean that more people in the network can are in agreement. Okay, we're making sure that more people, majority of the network are in agreement and the needs are satisfied. Non-iterative consensus is when you want to avoid so many rounds of talking to each other, and you want to basically elect someone to make the decision for you, right? So in most blockchains follow non-iterative consensus, where they elect a leader and the leader makes the decisions. So in the rest of the PPT, we're going to talk about consensus in blockchain systems. Okay, everyone with me so far? Okay, so I'm going to move ahead. So before we talk about consensus in blockchain, let me quickly talk about what blockchain is, right? For those who don't know, blockchain is basically a data structure. It is a data structure that has blocks in the form of a chain. That is, each block is linked to the previous block. And what does each block contain? They contain data, right? The data in these blocks is immutable and it is transparent. Okay, what do I mean? Once the data has been introduced in the block, it cannot be changed and anyone can view the data. So since it can be viewed, it can be audited. That is, you can track each data from present till the beginning, and it can be audited. So a blockchain is generally realized on something called a P2P network. P2P means peer-to-peer network, which means it's just like in the internet. Every node on the network is equal. There is no special privileges given to one node over the other node. Okay, and this data structure, this blockchain data structure, is maintained by everybody on the network because it is decentralized. There is no central server or central authority controlling this data. So everybody on the network has to maintain it. So this is the general flow of how a blockchain works. So as I said, there is some data which we're going to call transactions. So what exactly do we need consensus on in the blockchain? We need consensus on whether the transaction is actually right and in what order did they occur. The ordering of the transactions and the actual content of the transaction is what we actually have to agree. That is, everybody maintaining this blockchain has to agree on these two things. Okay, so how does that happen? In a non-iterative way, right? So in the network, we choose special peers, okay, who are called miners or validators, depending on which blockchain you're using. So these peers collate some of the transactions together in bundles called blocks. Okay, so after they formed a block, they participate in the consensus protocol that decides who is the next leader, and the leader gets to add the next block onto the blockchain, right? So they participate in the consensus protocol, and the consensus protocol elects a leader. Once the leader has been elected, the person who has won, the person who's been decided as the leader, will broadcast the block that they formed to the network. Everyone else, all the other validators, will verify if the content of that block is correct. If it is correct, then they add it to their local version of the blockchain, and this whole process will repeat, right? I hope everyone has understood so far. Please feel free to stop me and ask. Okay, so now we decided we saw how consensus happens, what is consensus in a blockchain, and how it happens in a non-interactive way. But why is it really important? Okay, blockchain, as I said, is a decentralized data structure, right? Everybody is maintaining it. There is no central person we can go to ask in case something goes wrong. So we need to, at every step of the way, we need to be sure that everyone else is working on the same input data. As I said, consensus has some input. People join, they make some decision on it, and that becomes the final output, right? So we, at every step, we need to make sure that everyone has the same input. They're all looking at the same data, and based on which the blockchain grows. So it helps us answer some very important questions, like, is the blockchain valid? Who gets to add the next block on the blockchain? What block gets added to the next block on blockchain? And is the data in the block correct? So these are very important questions that consensus helps answer in a decentralized way. So if consensus doesn't happen, I'll briefly talk about some adverse effects that can happen in the blockchain if we don't have consensus. Forks, double spend, selfish mining. These two I'll touch on in detail a little bit later. But let me explain what a Sybil attack and a 51% attack is. Sybil attack is an attack on a network in computer science. So Sybil attack is when one person in the network can duplicate their presence on the network. So they can spawn multiple nodes, making it appear like they have more presence on the network than they actually do, right? So that means they get more vote, they get more say on the decisions. So this is called a Sybil attack. So when we design a consensus mechanism, we should make sure that a Sybil attack cannot happen on that consensus mechanism and affect the decision of the consensus mechanism. Next is the 51% attack. 51% attack is when one adversary in the network can collude or bribe other people in the network and get a majority on his side and tilt the decision of the consensus in his favor. So these are two attacks that we have to be mindful of when we're designing consensus mechanisms. So we spoke about forks, but what exactly is a fork? So consider this peer-to-peer network here, as shown here. Okay, and this is the blockchain so far. So miner Alice, or validator Alice, thinks that she has won the election and she is the leader, and she has created her blue block over here. Okay, now what happens is she is sending this blue block to everybody else on the network. But before it could reach everybody on the network, miner Bharat thinks that he has won the election and he has generated a red block. Okay, and he is also broadcasting this block to everybody on the network. Okay, so parallelly, there are two valid blocks that are propagating on the network. So what happens here? Some people would have seen Alice's block first, and some people would have seen Bharat's block first. So the network is divided. Okay, they choose to accept the block that they saw first, and there are two absolute views of the blockchain. So this leads to division of the network, which leads to which basically affects security of the network. They are not in consensus over here. So a chain is stable only when all the miners are in consensus and united in extending the chain with a common prefix. Okay, I hope that makes sense. So we want, as I said, the consensus mechanism needs to have everybody should be seeing the same input for them to decide on the output. Okay, so this scenario where there's a bifurcation in the chain is called a fork. And so how do you resolve a fork? You have to wait. The network is divided, and one person, Chandru, who's working on the blue block, has found the next block on the blue block, and finally this chain has grown a little bit longer. So therefore, everyone has accepted Chandru's block. But there was a brief period of time where the chain was not in consensus. So now the chain has become stable again. So this stability translates to better security. So we need, if in case of fork, we need it to be resolved in a fast way. Okay, so now we'll talk about different types of consensus mechanisms out there. in blockchain, basically. So the most common ones that are actually tested at scale are proof of work and proof of stake. So we're going to be talking about those in a little bit more detail. But honestly, there are so many, there are N consensus mechanisms, and all of them have their advantages and disadvantages. But honestly, I don't think anyone needs to know all of them in detail. On a need basis, you can explore them, but I'm going to just touch upon them briefly. So let's talk about proof of work. Proof of work was the first consensus mechanism developed for the blockchain. It came about for Bitcoin blockchain. So what is proof of work? Proof of work is also called the Nakamoto consensus, named after the person who created Bitcoin, called Satoshi Nakamoto. So this is a non-interactive election-based consensus where a person, they participate in the consensus mechanism to elect a leader who will earn the right to add the next block on the blockchain. So what is proof of work? Proof of work is basically a mathematical puzzle. Okay, the person who solves this puzzle first is given the chance to be the leader of the next block. And it is important, being a leader is a big deal, because if you add the next block on your blockchain, you get the block reward. And I think right now the block reward for Bitcoin is 12.5 Bitcoin, which is a lot of money. So you would definitely want to be the leader in the consensus mining, right? So in proof of work, solving this puzzle is not easy. Okay, it requires a massive amount of computational work to solve. For example, let me tell you how this puzzle works. There is something called the challenge, which is the previous block on the blockchain, the block that you're trying to extend. The previous block that everybody knows about is the challenge. Okay, so you have created your own block, right? You have created your own block on top of the previous block. So that is the challenge. And you add something called the proof, which is a single nonce value. Nonce is nothing but like a number, like any number, any integer, 1, 2, 3, it can be anything. So you add those two together and you perform a hashing algorithm. Hashing algorithm is very simple. Hashing is nothing but any input you give to a hashing algorithm, it will give you a fixed length output. It is a one-way function. That is, any input x given to a hashing function will produce an output y, and this output y is always of fixed length. If I give my name Ovia into a hashing algorithm, maybe the hashing algorithm will give me an output of, let's say, 10 bit string. If I give unit masters, it will also give me a 10 bit string. But one important property is it is one way. That is, given the 10 bit string, it is impossible to find out what the input string was. Okay, so this hashing algorithm will give me a 256 bit string. In this 256-bit string, if the network as a whole agrees on what the solution could be, I'm giving you an example. Let's say the first 40 bits, if it is 0, then that means you're the winner. Your puzzle is correct. So out of the possible values, 202 power 256 possible values, all the values that have the first 40 bits as 0 form this blue sector over here. So this is the only possible valid solutions to the proof of work puzzle that I just described. Okay, so if you are able to find such a solution, such a proof that generates the first 40 bits as 0 in this hash function, that means you have won this proof of work election. It is as simple as that. Okay, so to better understand, let's just say there is a block like this. Each block has a header and a body. The header will have some metadata about the block. It can be the pointer to the previous block, when it was generated, and things like that, some link to the body. And the nonce value is the proof of work that I just described. So every time you want to generate a new block, you have to keep changing this nonce value till you find a solution that matches the first 40 bits as 0. That means you have found the solution to the proof of work person. Can you see how this is so computationally intensive? You don't know which nonce value will give this answer. So you have to keep trying one after the other by brute force, okay, which is why it is computationally intensive. And it's not only you trying, everybody on the network is trying to mine the next block on the blockchain. So it is very computationally intensive. I mean, it's actually the power used for mining Bitcoin is pretty high. Like, I think I have some stats in the next slide. Let me just go forward. Yeah, so sorry. So, okay. Confirmation time and double spend is a very important problem that exists in proof of work blockchains. Confirmation time is nothing but the time that you wait to get, so let's to get your goods or services after paying for it. Let's say you go to a coffee shop, okay, and you're buying a cup of coffee. You pay the waiter in Bitcoin. Okay, let's say you pay them in Bitcoin. After paying them in Bitcoin, the time that the waiter has to wait till he accepts your Bitcoin, till he's sure that the Bitcoin is actually being paid to him, is the confirmation time. This sounds silly because we are used to paying with MasterCard, Visa, that is instantaneously confirmed for us. Within a matter of seconds, after every payment, we get what we paid for, right? But in blockchain and cryptocurrency hasn't advanced to that stage where such instantaneous transactions are possible. So in Bitcoin, actually, you will have to wait a significantly long amount of time for this to happen. Okay, so let's say a transaction has happened. First, the transaction should enter a block, right? That will take some time. And after it is entered, research has told us that this 6 blocks have to be added to the chain before we can accept that transaction, which is insane because each block in Bitcoin takes about 10 minutes to arrive. So after 10 minutes, you are waiting for 6 more blocks, which is 60 minutes. You're waiting for 60 minutes to confirm this transaction. So it's like paying for a coffee, waiting 60 minutes in that cafe for your transaction to be accepted, right? Why do we have to wait so much? If the transaction has been added to a block, right? Blockchain is immutable. Why should we wait? Because of this double spend attack. So what is a double spend attack? So it is possible for an adversary who has some amount of computational power to secretly mine a different chain and release it after this block has been accepted and completely cancel out this block and make everybody choose this block. Right. So what he will do is he'll secretly mine the chain after start mining the chain after the transaction is initiated. And he waits for the transaction to get accepted in a block. Accepted, that is after the 6th block. And once it's accepted, he releases his private chain. And now he can double spend this coin. So he's already, let's say he paid for this coffee. He's got the coffee at this point. But now he's released a completely different chain. And it's like that transaction never happened. So he can spend those coins again. This is a double spend attack. So Satoshi, who created Bitcoin, said that if the adversary controls 10% of the whole computational power, then if you wait 6 blocks, then he has with 99% probability this kind of attack won't happen. That's why he asked us to wait till 6th block. If it hasn't, if you accept the transaction anytime earlier, then the probability of this transaction confirming goes down security. Probability of this attack increases. Okay, this is the double spend attack, and this defines the confirmation time. That's why we have to wait so long in Bitcoin. Another kind of attack in proof of work system is the selfish mining attack. Selfish mining attack is very similar to the double spend attack, where here the adversary just wants to get block rewards. In the double spend attack, the adversary wanted to double spend his coins. Here he just wants the block reward. So a blockchain is happening like this. Adversary is always secretly mining a chain, and once his chain grows a bit longer, he will release it and make all the honest nodes mine on his chain, and he keeps going like that to gain as many unfair rewards as possible. So these are kind of advanced attacks, but just on a high level, I've tried to explain. Please ask me if you have any doubts. But these are some big attacks that are still prevalent in proof of work blockchains. So to recap, proof of work blockchains are extremely secure and one of the most well-tested consensus mechanisms in blockchain networks, right? It is very difficult. Sybil attacks are not possible because you are actually spending computational work, right? You cannot just duplicate yourself because the amount of computational effort you hold is still limited. 51% attack is not possible because you have to take 51% of the entire computational effort in the network, which is a lot, right? So it is extremely secure and it is battle tested, but it is a luck game. Everyone is spending a lot of energy, computational effort, and only one person wins. All the others' energy is wasted. And as I said, it is proof of work mining can consume 0.5% of the global electricity production. That is just ridiculous because that's enough to power countries like Sweden and Malaysia for a year. So it is not exactly the most green kind of consensus mechanism, but it checks most of the other boxes. So people still use it. So Bitcoin and all of its folks, that is Bitcoin Cash, there are other things based on Bitcoin. All of those blockchains use it. Dogecoin, Primecoin, Litecoin, all use proof of work. And proof of work also has many derivatives like proof of useful work. Instead of just randomly just brute forcing nonce, can you prove that you've done some useful work? There's hybrid proof of work, time delay. So there are so many consensus that have spawned off proof of work. Ethereum was also using proof of work till very recently. I think in September, they moved to proof of stake. So what is proof of stake? So any questions on proof of work? Okay, cool. So proof of stake came because of how energy inefficient proof of work was, just to make it a bit greener. It is not the most perfect consensus mechanism. It also has flaws. But let's talk about what proof of work is. So in proof of work, we kind of prove that we have done so much computational work, right? Here, we're not proving the amount of computational work we're doing. In proof of stake, we are proving that we have put so much money into the system. We have staked so much money into the system. Therefore, we have the right to mine the next block on the blockchain. That is, our stake implies that we want to participate in the well-being of this consensus system. So please pick me as the next block, next leader, right? That's what we're saying. So here, you don't get any block reward. That was also a policy change that happened really recently. So every person who collects, mines the next block on the blockchain, the leader will only claim the transaction fees inside the block. This is, as you can see, it is very energy efficient. People are not doing useless brute force work, and one leader is chosen at every interval. So that is known a priori. But it is not as battle tested as proof of work. So it is a relatively new one. It is still much better than other consensus mechanism, but it is still not as tested as proof of work. So how do you participate in proof of work? How do you become a validator? So I'm going to talk in terms of Ethereum, which is the largest proof of stake system. So here you call the person participating in the consensus as a validator. In Bitcoin, you call the person participating in the consensus as a miner. Here you call them a validator. Okay, so how do I become a validator in Ethereum? I have to stake 32 Ether into a contract. Okay, after I stake this much Ether, I'll be put into an activation queue, which limits the rate of new validators joining. So with every added validator, the chance of the next validator getting added reduces. Okay, so once the validators are activated, then they have to participate in the consensus mechanism called proof of stake, and they start receiving blocks. So in Bitcoin, we said that because of forks, each block has to be 10 minutes apart, and our confirmation time is also dependent on that. 6 blocks from that, so 60 minutes. So that the block interval was decided based on other factors. But in proof of stake, it is not like that. Proof of stake, the block interval is fixed, right? The time taken, so Ethereum divides it every 12 seconds into a slot and every 32 slots as epochs. At every slot, one validator is randomly chosen among all the activated validators. So once when you're chosen at that epoch, you will know that you're a validator. Okay. If you are a validator, you've already created a block, right? That you want to propose. You will propose that block. But what do you mean randomly selected?
Okay. I'd like to interrupt you for a moment. So I just wanted to say that we have 15 minutes left and we still want to have the questions. So if you could start wrapping up, that would be amazing.
Sure. Cool. So yeah, so how do you randomly choose a validator? Based on the amount of ether they've staked. The larger the amount of ETH staked gives you more chance, and the age of the ETH staked. How long has the ETH been staked? And if there are more than one person with the same kind of parameters, you add some element of randomness to choose the validator. So after he's proposed the block, other people will re-execute the transactions in the block and verify whether the proposed block is right. And if it is right, they attest it by voting for it. And that's how the whole process of consensus happens in proof of stake. So there is a problem here called nothing at stake problem. So at the slot start, let's say a validator has been selected. Now in proof of work, he had to spend some energy to mine every block. Here, once he's validated, once the validator is chosen as the leader, he can just mine as many blocks as he wants. So that can lead to forks. So as I said, there is a problem of nothing at stake problem in proof of stake. And every validator has staked ETH, so that is locked up ether that is out of circulation. And there is a rich get richer problem, where if you have more money, then you can participate in consensus more, you can gain more rewards, and that keeps that's just a downward spiral. Okay, so now we have covered the two main consensus algorithms. I'll just briefly tell you about other kind of consensus in the next few minutes. There is a delegated proof of stake where the validators don't participate in any randomness. They are chosen. You can vote for your validator, and the validator can share some rewards with the other person. There is proof of space, time, and capacity, where instead of staking coins, you stake your memory, right? You say that I have given this network so much memory space for a particular amount of time, and that's why I have the right to mine the next block on the blockchain. So Chia and Filecoin are good examples of this. There is proof of weight, which basically says any kind of stake. You don't have to stake the native token. You can stake anything to earn the next right of the blockchain, right to add the next block on the blockchain, which is used by Algorand. There is proof of burn, which I personally think is a bit silly. It just says that there is an address. It's like an reversible transaction. You'd send money to that address, it never comes back to you. You're burning money, basically. You send more money to that burnt address, then you get more chance to mine the block. Yeah, which is, I don't personally agree with this, but there's proof of elapsed time, which is pretty interesting, which just says that you, for every miner, tosses a coin and randomly generates some period of time he has to go to sleep. And after waking up, if he's proved that he has slept for that time, he gets to mine the next block on the blockchain. There's proof of activity, which I'll skip. Proof of authority is for permissioned blockchains, where you select validators who are not anonymous. You know they've been their trusted nodes in the network because they've staked their reputation, and you let them mine the next block on the blockchain. PBFT is the type of iterative consensus where people have a conversation and they decide on the decision. Hyperledger uses this. Ripple also uses a iterative consensus called federated byzantine agreement, which basically says There are a couple of trusted nodes. You keep giving them data and let them vote on it. If they vote, whatever transaction gets the most votes, they gets to be a part of the blockchain. And hash crabs and us, I can skip this for now. So that's it from me. I hope you all got a good idea of consensus mechanisms, and I'm open to questions. Thank you.
Amazing, amazing, Ovia. Thank you for sharing incredibly informative presentation with us today. Before we jump into the question section, I would love to know how come you've ended up researching this work, and why do you think it's important?
Yeah, so my research is on scalability of proof of work blockchains, and consensus is a very important aspect of any blockchain system, because I personally believe in decentralization. I'm a decentralization maxi. It's been too long where we've put our trust into trusted authorities. We're paying too much transaction fees, and we're completely dependent on a few very rich and powerful hands in our world. So I think everyone deserves equal chance, and they should trust that they're being fairly represented. So that's why decentralization is important. And in a decentralized world, how do you make things work? How do you agree on protocols? How do you develop a systematic way of governance or to do anything, right? So this is where consensus is important. So there is still, I've talked about so many consensus mechanisms for the blockchain, but there is still no ideal one, right? And so that the pursuit continues to find the ideal consensus mechanisms.
Amazing.
So guys, if you have any idea, then please go publish it, put a research paper on it.
Yes, there's so much still research that can be done. And I see that there are a couple of people that have raised their hands. So I'm going to first unmute Victor. And Victor, go ahead and ask your question.
Awesome. I just need a few minutes at the end to talk about the Phoenix Guild. So please do give me like 2 or 3 minutes at the end, so we can wrap.
Sure.
Is that
sure?
okay?
That sounds great.
Sure. Okay, I'll take questions now. One
awesome.
second. Let me just. Awesome.
Okay. Victor, I've just unmuted you, so go for it.
Okay. Sorry, can you hear me?
Yeah, I can hear you, Victor.
Okay, my question is this proof of stake, you understand? You know, it is based on those who have much token or much token on in their wallets. Those who have like the larger amounts can actually have the chance to be a validator. You understand? So is that not like bringing us back to centralization? You understand? Instead of decentralization, like having everyone being in charge of, like having everyone governing the whole network rather than some few people governing the this thing, being a validator. So I don't know, is it not bringing like this sense of centralization back to blockchain?
I agree with you. You're talking about proof of stake, right? Yeah, I agree with you. So as I said, the rich keep getting richer in that problem. So the Ethereum has put a limit on it. They have said you can only stake 32 ETH. But what is stopping people from creating multiple validator nodes, right? I can put 32 ETH across multiple validators and still earn it. And one more thing is, Ethereum has also tried to tackle that by making the validator acceptance process a bit hard. But yeah, you're right, it is possible. There is a non-zero probability that one person can get like an unfair advantage. So as I said, it's not perfect, but it has worked for some time. So,
but we still can't trust the body. We still can't trust them since they are like humans. It's not robots. You understand? It's not like programmed smart contracts. They are people that they can change their mind one day and just begin to receive transactions that were not actually on the chain.
No, the validator selection process is completely automated. It is done on chain. So
okay.
It is, so there is no human intervention in any of this, in this protocol at all.
All right. Thank you.
Okay, Thank you so much for your question, Victoria. So Simotaro has raised their hand. So Motaro, I am unmuting you as well. Go for it.
Hello, everyone. Good day.
Hello.
Just a quick one. Victor has asked similar question as I wanted to ask before, but in addition, I still have one more doubt, though I'll just digress a little bit from what I read online some times ago. You made mention of consensus mechanism in blockchain. So my question is Stellar consensus protocol a type of consensus mechanism? Stellar consensus protocol, is it a type of consensus mechanism in blockchain?
Stellar consensus.
Yes,
I'm
yes.
sorry, I haven't heard of this, but please enlighten me.
Oh, okay. I read about there is a particular blockchain, a coin, they implemented it, this Pi coin. I don't know if you've heard of Pi coin. So I read
Filecoin?
yes, I read their white paper.
Okay.
So they said they use this stellar consensus protocol as against the usual protocol, like the proof of work protocol that is used in Bitcoin. So I didn't really get clear picture about it. But since you've not heard of it, there is no problem. Maybe I will still do more research and find out about it on my own.
Sure, I'll go and see what that's about.
Yeah,
as well.
thank you.
Amazing. Thank you so much for your question. I'll also take now a question from the chat as well. And I see that Mutairo asked, won't proof of stake eventually become a centralized system since the decision making is based on a few stakeholders? What are your thoughts on it?
I'm sorry, can you repeat the question?
Won't proof of stake eventually become a centralized system since the decision making is based on a few stakeholders?
Yeah, so Ethereum combats that by, as I said, by limiting the number of stake and by making the process of adding validators extremely hard. And the system is, the blockchain network is significantly large. So we can avoid centralization to an extent, but you never know, right? If you control enough validator nodes, that is 51% of the validator nodes, which is a really big number. You can't control 51% of all the staked ETH. So it's just a law of large numbers. So that, yeah, it's still difficult.
It's still difficult, but it's definitely we're definitely getting there. And what about Ruben? I've just unmuted you and would love to hear your question.
Thank you very much for the opportunity. Can you hear me?
Yeah, I can hear you.
I just want to extend Victor's questions. That proof of stake, since it's based on who contribute more, will it not encourage capitalism?
Capitalism in what way? I didn't quite get the question.
I mean, those that have more token, the bourgeois will take over because they will now invest more in it and now have more control.
Yeah, but see, there is no one deciding who the validator is, right? You are allowed to stake 32 ETH, but that is still like a finite amount of money. It's not, you can't just throw your money around to become a validator, because all of this is automated. There is no person sitting behind that blockchain deciding whether you can be a validator or not. You can't bribe that person. So if you have 32 ETH, then you can become a validator. You have more than 32 ETH, you can try to have more validator nodes, but there is something stopping. The protocol has like a mechanism to prevent that.
Thank you. Thank you. That is all from me.
Okay.
Thank you. Thank you so much, Ruben, for your question. So running out of time right now. Thank you everyone for your questions. And also wanted to ask right now, Ovia, if people wanted to connect with you, what would be a good way?
Yeah, I have shared my Twitter and LinkedIn. I'm fairly active in these two places. So please feel free to connect with me and let's chat more.
Amazing, amazing. So do connect.
I will just put my my Twitter here on chat box.
Yeah, amazing. So if
I just want to take a few minutes to explain the community that I come from, and it may be good for other people who are interested to join or be a part of it. They can benefit from it. So can I just take 2 minutes to explain?
Sure.
Awesome. I'm just going to share my screen again.
And Ovia, sorry, when you're sharing, you're not sharing the messages to everyone. You're just sharing with me.
Okay. Do you mind just copying it and pasting it again?
I'll do that right now. Yeah, I'll do that right now. So go ahead.
Right. Okay. Thank you. Cool. Can you see my screen?
Yes, all good.
Yeah, hi. I'm part of this community called the Phoenix Guild. We're basically a non-profit. And our mission is to create and onboard the next million women and non-binary builders in Web3. We say that we want to build women and non-binary. We definitely want to see more female, feminine, and non-binary presence in most companies, which has a very bad gender ratio, but we're open. Our community and our work is open to everyone, so you can still be part of Phoenix Guild. And we say builders, which means we're not focused on only the technical people. Anyone who wants to build, no matter what background you come from, if you have an idea and if you want to build something, yeah, this community is for you. So we want to see these women and non-binary folks represented in the C-suite of companies as senior leadership roles and position in Web3. Web3 is positioned in a very unique way right now. The industry is just beginning, and there is scope for everyone to come in and make a good career. But we will help them by we're focused on education. We give them material, we promote opportunities in our community. So if you're looking for jobs, if you're looking for internships, people to help you build your project, educative materials to learn. Yeah, so we provide all of that free of cost. So what we've done so far, we've done some Solidity boot camps. We've done IRL workshops and tech talks. We have many study groups based on whatever you want to learn. There are a lot of master classes. We conducted the first ever female all female hacker house. And even ETH India just happened last week, and we had a hacker house there as well. So what is in store? We have an ongoing Solidity bootcamp. If you can scan this code to get the material. It's free for everyone if you want to learn Solidity. We have a chapter program, and our Pune chapter is hosting an event with Chainlink and StackOS. We regularly conduct proof of community workshops with Shardium, which is a layer 1 blockchain. And we're going to be at ETH Denver, so watch out for that. So how can you be a part of our community? We have our Telegram link over here. Please scan this to become a part of our Telegram. This is our Twitter. You can follow it. And if you want to be a part of the chapter lead program, please apply in this link. Yep, that's it from me.
Amazing. Thank you so much for sharing this. This is a great initiative. I've actually been part of Phoenix Guild Telegram for a while and been incredibly impressed.
Awesome.
Are doing in the women empowerment space in Web3. So do check out Phoenix Guild, do check out their links, join their chats, and it's an absolutely amazing community that you've built. All right, so I think it's time to end the session. If you do have any further questions, do reach out to Ovia over Twitter or LinkedIn. The links were posted earlier in the chat. Thank you so much for attending. I hope you have a lovely week, and we will see you tomorrow in the demo session.
Okay.